Hey guys, welcome back. This is Srivat Sain studying in Sri Venkateshwara College of Engineering, and this is my video assignment regarding the subject of mathematics M4. And I'm here to present to you about the partial orders and Hasse diagram in mathematics. Introduction to partial orders. The partial orders are a type of binary relation that defines a comparison between elements. They must satisfy three properties: reflexivity, antisymmetry, and transitivity. Partial orders are essential in various fields like computer science, mathematics, and scheduling problems. So, as there's an image here, uh, like which makes sense like a text. Partial ordering relations. So there are three conditions present here. The first condition is R is reflexive, that is X R X is true for all X belongs to X. R is antisymmetric for all like X implies X is equal to Y. And then R is transitive when X relates to Y relates to Z, and relates to Z. That is the transitive property. So all the three conditions has to be satisfied be in order to be a partial order. So the properties of partial orders are reflexivity means every element is related to itself. For an element A is less than or equal to A. Antisymmetry states that if A is less than or equal to B and B is less than or equal to A, then A must be equal to B. So transitivity implies that if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C must hold true. So the same thing is given in the right side section 2 about reflexivity, symmetry, and transitivity. Examples of partial orders. The subset relation among sets is a common example of a partial order. The divisibility relation among integers is another classic example. The relation of less than or equal to is a total order, which is also a partial order. So in the right side, the image is going to be representing the partial order to you. So introduction to Hasse diagrams. So a Hasse diagram is a graphical representation of a finite partially ordered set. It simplifies the visualization of the relationships between elements based on their order. Hasse diagrams omit transitive edges, showing only the immediate relations between elements. Drawing Hasse diagrams. To draw a Hasse diagram, begin by identifying the elements and their relationships with each other numbers. If, for example, the image is given in the right side, arrange the elements vertically so that if A is less than or equal to B, then A is placed below B. Eliminate transitive relations to simplify the diagram, keeping only the direct connections. So here 6 is self, 6, 4, 5, and 7 are self-looped. That means 6 comma 6 is a set. So 5 goes to 6, 4 goes to 6. So the in degree for 6 is 1, and the in degree for 4 is 0. For in degree of 5 is 1, and in degree of 7 is 3. And likewise, whichever is coming into it is in degree, and whichever is going out of it is out degrees in the Hasse diagrams, or wherever it is. So example of Hasse diagram, consider the set 1, 2, 3, 4, 6, 12 with the divisibility relation. So the Hasse diagram would show 1 at the bottom and 12 at the top with edges, um, 12 at the edges connecting elements based on divisibility. This visual representation helps to quickly identify the hierarchy of the elements. Draw the Hasse diagram for the divisibility relation on the set 1, 2, 3, 4, 5, 6, and all of these, and you have to explain. So it's just a question for us to have the practice and have a hold on it. Applications of Hasse diagrams. Hasse diagrams are used in computer science for data structure organization and retrieval. They are also employed in lattice theory to study the relationships between different algebraic structures. Additionally, Hasse diagrams assist in project scheduling and task prioritization. Limitations of Hasse diagrams. The Hasse diagrams are often limited to finite sets, and infinite sets complicate visualization. They can become cluttered and difficult to interpret when dealing with many elements. Some relationships may be obscured when transitive edges are removed, potentially causing misunderstandings. So here, now we know what Hasse diagrams are using the image. Comparison with total orders. In a total order, any two elements are comparable, while in a partial order, this may not be the case. Hasse diagrams for total orders are simpler as all elements can be connected directly. This difference results in a more comprehensive understanding of a structure in total orders. So let's dive into the conclusion and summary. Partial orders and Hasse diagrams provide essential tools for organizing and visualizing relationships. So understanding their properties and applications can enhance problem-solving skills in various fields. This foundational knowledge can lead to further exploration of advanced topics in other theory and mathematics. Thank you, guys.